So far, we have discussed some properties and some theorems on characteristic functions. Mainly, the most important theorems are inversion theorems and Bochner's theorem. One interesting thing that I would like to point out once again, that in the inversion theorem and the Bochner's theorem, in these theorems, we have actually used the convolution of a normal random variable and then make that normal variable to converge to a degenerate variable. That means, we are making that sigma, which is a standard deviation of the normal variable, goes to 0. So, this is a nice technique which we can apply in many areas or in many problems. So, now we can think of when I say that sigma goes to 0. So, another kind of limit we can think that if there exists some kind of sequence of random variables or sequence of distribution functions or sequence of characteristic functions. So, the question is, can we say something or can we have some results or theorems or some interesting feature with respect to this sequence of variables or sequence of characteristic functions. So, today we will be discussing and study this sequence of random variables along with their sequence of distribution functions, and we will also consider the sequence of characteristic functions. And when we have a sequence of anything like any functions, we should be able to give some idea about the limits of that sequence. Now, naturally, we have already seen in many theorems with respect to sequence of distribution functions, where this concept of limit is concept of limit holds only under certain conditions. So, we will be discussing in detail this kind of sequence and their limits and whether they converge to some another function. So, we will be discussing that. Characteristic functions 5. Just now I mentioned that we will start with some concept of convergences corresponding to sequence of random variables or sequence of distribution functions. So, the first definition that I will consider is that suppose x n be a sequence of random variables and it converges to x in distribution. So, question is, what is the definition of that? So, a definition is a sequence x n of random variables converges to a random variable x in distribution if f n x tends to f x. Now, f n x is the sequence of distribution functions corresponding to this sequence of random variables x n, and f x is the distribution function corresponding to the random variable x to which this converges. Now, this convergence holds at every x at every continuity points of f. C f denotes the set of continuity points of f, and we write that x n converges to x weakly. That is why I use the letter w, or x n converges to x in distribution for D, and x n converges to x in log. So, this is the definition of convergence in distribution. Now, we know that x n is a random variable. So, corresponding to the random variable, we know that there always exists a distribution function, and hence we can define convergence in terms of the distribution functions. Now, one can also say that since this is a random variable, we can define several probability events corresponding to this x n. So, can we define something in terms of probability events? That means, can we define some similar type of convergence relating to this different probability events? And that's where we get the second type of convergence, which is defined as a sequence x n of random variables converges in probability to a random variable x if probability modulus of difference of x n minus x greater than epsilon that goes to 0 as n goes to infinity for every epsilon greater than 0. That means, so if we consider an event, and if we consider that event with respect to x n and x and take the difference, and suppose probability of such events, so that x n minus x greater than mod of that greater than epsilon if this probability goes to 0, that means when n goes to infinity, practically we are getting the same probability. So, this goes to 0 as n goes to infinity. So, we write that as x n converges to x in probability. So, these are the two definitions, two notions of convergence. One is convergence in distribution, which is related to the distribution function of the random variable, and one which is convergence in probability, which is relating to the probability defined using the random variables or the sequence of random variables. Now, the question is whether there exists any relation between these two. The answer is fortunately yes, and it can be shown, we will discuss this later, that if x n converges to x in probability, this will always imply that x n converges in distribution to x as n goes to infinity. Before stating one result relating to the sequence of characteristic functions, because since we have a sequence of distribution functions, we can always define a sequence of characteristic functions corresponding to each distribution function. So, before stating one important theorem, I am going to state a couple of theorems which will be used to prove the theorem with respect to characteristic function. So, one such theorem is called Montel-Helis theorem. It says that every sequence of distribution function f n x of uniformly bounded function or non-decreasing functions contains a subsequence f n k which converges weakly to a non-decreasing bounded function capital F x. Now, this is true for any uniformly bounded non-decreasing function, not necessarily distribution function, but if f n x is are distribution functions, then f must be the convergent, the limiting distribution limiting function f is also a distribution function, provided f n infinity goes to f infinity and f n minus infinity goes to minus f minus infinity as n goes to infinity. So, although Montel-Helis theorem is nice about and holds good for any type of uniformly bounded non-decreasing functions, it is also true for distribution functions, because they are naturally bounded and non-decreasing. Next one is Helis' second theorem. It says that suppose small f x be a continuous function and assume that f n x is a sequence of uniformly bounded non-decreasing functions which converges to some function capital F x at all points of x which are continuity point of f and which is nothing but the intersection of continuity points of f and the interval a b, and of course, a b both must be continuity point of f. Then limit n goes to infinity a to b f x d f n x equals to integration a to b f x d of capital F x. So, this gives us an idea about the convergence of a non-decreasing uniformly bounded sequences, and in some sense with and considering another continuous function, but remember this will converge. It is enough to get this convergence at continuity points of f intersection with the interval of a b. So, a natural question will arise that is it possible to extend this limit a to b to minus infinity and infinity? So, that is a natural extension of this theorem, and fortunately again the answer is yes, which gives us extended Helis theorem, or which is known as Helis-Bray theorem. Here suppose f x is continuous and bounded within the real line, that means for every x in the real line minus infinity to infinity, and f n x is a sequence of uniformly bounded non-decreasing functions which converges to some function capital F x at each continuity point of f, that is x for every x where x is a continuity point of f. Also suppose that as n goes to infinity, f n minus infinity equals to f of minus infinity, and limit n goes to infinity, f of infinity equals to f n of infinity equals to f infinity. or in other words we can get f x goes to 0 as x goes to plus infinity or minus infinity. But remember, if this holds, then of course the boundedness of f would be superfluous. And under these conditions, this theorem states that under these conditions it can be shown that limit n goes to infinity, integration minus infinity to infinity f x d f n x equals to integration minus infinity to infinity f x d f x. So, the same kind of theorem holds even when the range of integration is limits of integrations are minus infinity and infinity. Now, we will use these theorems in proving the next theorem which is related to sequence of characteristic functions, and this is the theorem which is known as continuity theorem of characteristic function. So, let us first state this theorem very clearly. Let f n be a sequence of distribution functions. So, here we are considering only the sequence of distribution functions, not any general uniformly bounded non-decreasing functions. Naturally, because we can always define characteristic function corresponding to each f n, which must be a distribution function. So, let f n be a sequence of distribution functions and phi n be the corresponding sequence of characteristic functions. Suppose that limit n goes to infinity phi n t equals to phi t, and this exists. So, this limit must exist for all t lies between minus infinity to infinity, and phi is continuous at t equals to 0. You see this t equals to 0 when we discuss phi comes very frequently in the discussion of characteristic functions. Then, so if this conditions hold, then there exists a distribution function capital F which has phi as its characteristic function, and capital F n converges to capital F completely. That means, the question that I asked at the very beginning, that if this limit exists, limit of sequence of characteristic functions exists, then can I treat this phi t, which is the limit of the sequence of characteristic function, can I treat this phi t as a characteristic function of some random variable or some distribution function? So, this theorem ensures that yes, we can do that. So, there exists a distribution function f which has phi as its characteristic function, and interestingly this f is nothing but the distribution function where f n, the sequence of distribution function, converges. On the other hand, conversely, if f n converges to capital F completely, then phi n converges to phi t, which is the characteristic function of f. So, there is a nice relation between the sequence of distribution functions and its limits with the sequence of characteristic functions and its limit, and incidentally this limiting distribution function, that is f, and this limiting characteristic function, that is phi, has some relation between them. In fact, phi is the characteristic function of capital F. So, let us give an outline of this proof. So, as I already mentioned, that to prove this theorem, I will repeatedly use the previous theorems like Helis theorem and extended Helis theorem, and obviously Frobenius theorem, because it involves many integrals. So, first take f x equals to e to the power I t x, and note that limit f n, limit n goes to infinity, f n infinity equals to f infinity, and limit n goes to minus infinity, f n of minus infinity equals to f of minus infinity. Then immediately, so since these two conditions are mandatory for extended Helis theorem to apply, so we can get immediately by applying extended Helis theorem that limit of n goes to infinity phi n t, which is nothing but limit n goes to infinity integration minus infinity to infinity e to the power I t x d f n x equals to integration minus infinity to infinity e to the power I t x into d f x. This is just direct application of extended Helis theorem, and we see that this is nothing but the distribution characteristic function of capital F, which is denoted by small phi t. So, this proves the necessity part. So, as we have already seen that this continuity theorem actually states some necessary and sufficient condition and for the limiting function to be a distribution, to be the characteristic function of a limiting distribution function. So, let us now consider the sufficiency part. That means, consider phi n to be a sequence of characteristic functions corresponding to f n, phi n goes to phi t and continuous at t equals to 0, that is given. Along with that, modulus of phi n t less than equals to 1, that means, this is bounded for every n, bounded by a constant for every n. This three imply that 0 to v phi n t dt converges to 0 to v phi t dt when v is finite, as obviously n goes to infinity. So, for any subsequence n k, we have integration 0 to infinity phi n k t dt. Now, what is phi n k t dt? This is nothing but characteristic function of f n k. So, we can write this as 0 to v, then integration minus infinity to infinity e to the power I t x d f n k x, which is the characteristic function of f n k into dt. Now, again we have two integrals. So, immediately we have one option, one major trick, that just to use Fubini's theorem. Obviously, all the conditions of Fubini's theorems are being satisfied, and so we can immediately apply Fubini's theorem and change the order of integral. So, once we change the order of integral, this e to the power I t x depends on t. So, we first integrate 0 to v e to the power I t x dt, and we have minus infinity to infinity d f n k x. So, this becomes minus infinity to infinity e to the power I v x minus 1 by I x into d f n k x. So, we can write phi n k t, integration of phi n k t from the within the limit 0 to v with respect to t is exactly equals to minus infinity to infinity e to the power I v x minus 1 by I x into d f n k x. By Helis' first theorem, f n has a subsequence f n k which converges to g weakly, that means in distribution. And again by Helis' second theorem, as k goes to infinity, we can think that 0 to v phi n k t dt converges to integration 0 to infinity e to the power I v x minus 1 by I x d g x. So, Helis' second theorem states that this should be with respect to the limiting distribution function or the g x. Let let small phi capital G t be the characteristic function of capital G. Now, similar to 2, that means previous equation in the last page, 0 to v phi g t dt equals to the same thing using the same trick of Fubini's theorem, minus infinity to infinity integration e to the power I v x minus 1 by I x into d g x. So, by equation 1, equation 3 and 4, we have integration 0 to v phi t dt equals to integration minus infinity to infinity e to the power I v x minus 1 by I x into d g x. And from 4, this second integral is nothing but 0 to v phi g t dt. Now, it is clear that both extreme sides are differentiable at v equals to 0, as the integrands are continuous at t equals to 0. So, by differentiating at v equals to 0, we get immediately 1 which is equals to phi 0, which is again equals to phi g 0, and again just a little bit of manipulation will show that this is exactly equals to g of infinity minus g of minus infinity. And since 0 less than equals to g minus infinity less than equals to g infinity less than equals to 1, so from this line we must have g of infinity equals to 1 and g of minus infinity must be equals to 0. Otherwise, we cannot get this difference to be equal to 1, and they are all positive. Therefore, we can immediately see that capital G is a proper distribution function. Now, if you look at the equation 5, it is clear that the right hand side of equation 5 is differentiable for all v with derivative phi capital G of t. but interestingly left hand side of equation 5 does not depend on g and differentiable for all v. Hence, we can get phi t equals to phi g t, and if you recall the uniqueness theorem, by uniqueness theorem g is nothing but the unique proper distribution function for every subsequence of f n. So, what we get is that the limit can also be treated as a characteristic function corresponding to the limit of the sequence of distribution functions. So, which is actually the famous continuity theorem and has many applications in proving many results, many theorems in probability as well as in characteristic functions. So, today we have introduced the concept of convergence in distribution, that means corresponding to a sequence of distribution functions. We have also introduced the concept of convergence in probability and whether there exists any relationship between these two. We have also introduced a sequence of characteristic functions, that means when there is a sequence of distribution functions, we can naturally define a sequence of characteristic functions corresponding to the sequence of distribution functions. And one important theorem that we have discussed, which is continuity theorem, that deals with the limit of the sequence of characteristic functions, under what condition it holds, and most importantly whether the limit of the sequence of characteristic function can be treated as a characteristic function corresponding to a distribution function. If we can, and we have seen that it is possible. So, the limiting form or limiting function of the characteristic sequence of characteristic function can be treated as a characteristic function, and we can naturally determine the distribution function corresponding to this random corresponding to this characteristic function.